we have a long-time collaboration between our theoretical team and experimental team by Denis, and during his talk he make accent on the application of curvilinear magnetism to the shapeable magnetic electronics. And during my talk I will try to describe some fundamentals of curvilinear magnetism, will describe the current stage, the current challenges, future challenges of this subject, and my main focus will be on novel physical effects caused by toroidal curvature and topology in conventional magnetic materials. Okay. So curvilinear magnetism is a very young and modern direction in the magnetism. The first review of curvilinear magnetism appears just 7 years ago. And there are a lot of different curved materials, a lot of different effects. And during the talk, I will try to explain what new physics appear if we curve the magnets. So first, what happens if we extend the conventional two-dimensional nanomagnets to the three-dimensional nanoworld? In this sketch, you see a number of different magnetization textures, and they appear a number of effects, very interesting effects, which will be considered. The magnetism roadmap in 2020, it's selected at curvilinear magnetism as a new perspective direction, and the perspectives of the curvilinear magnetism were directed in 2021. So let me start with some very simple ideas. What happens? What is the origin and new physical effects which appear in curved magnets? So typically, if we consider a flat magnet, it has a special inversion symmetry. For example, here on this sketch, you see the flat film when the top and bottom surfaces are typically identical. The situation drastically changes if we curved the magnets. So in this banded film, the inversion, special inversion symmetry becomes broken, and there appear local geometrical effects connected with this curvature. And it leads to appearance specific geometry guarantee interactions, namely geometry guarantee anisotropy and geometry guarantee chiral interaction. And as a result, this emergent interaction, they form this group of geometrical magnetic chiral effects. And the picture becomes more intriguing if we change the geometry not locally but globally. I mean, we change the topology, and due to the combination of these local and global geometrical effects, they appear new magnetization textures, which lead to a new direction, which is called topological patterning. To describe this, the physical ideas, I consider here a typical model of a ferromagnet with typical interactions, which consist of exchange, anisotropy, Dzelshinsky-Moria interaction, and magnetostatics. So the typical model of ferromagnets. But to understand the basic ideas of the curved magnetism, we consider a minimal model. We consider only exchange and anisotropy. While this model cannot describe all the curvature effects, it's enough to understand the basic ideas. Moreover, this model is quite general because it's described by the well-known Ginzburg-Landau function for the vector order parameter, and the approach which we consider, it gives a possibility to describe not only curvature in fixed magnets, but also in different systems with vector order parameters. So it describes also liquid crystal superconductors and other systems. How the curvature appears in this model. The idea is the curvature gets into the game due to the curvature, the geometry-dependent anisotropy. The anisotropy direction fills their geometry. For example, if we consider the curved wire, typically the anisotropy direction follows the tangential direction to this wire. If we consider the curved magnetic field or curved shell, the anisotropy direction is typically determined by the normal direction to this surface. Moreover, if the anisotropy is strong enough, it dictates that the assumable magnetization texture should be considered in the curvilinear reference frame. So it changes the symmetry of the system, and it can be illustrated in it appear in different interactions which break the symmetry due to the spatial derivatives. And very nice example, simple example, is the exchange interaction. If we consider an exchange interaction which is described by the functional which is isotropic in the Cartesian reference frame, the considering of the system in a frame of reference adopted to the geometry, it leads to the restructuring of all energy terms which fill the symmetry of this curved geometry, wires or shells. And you see that the exchange interaction, it can be presented in the as a three terms with different symmetry. The first one in naught is the common exchange interaction, which looks isotropic but in the curvilinear reference frame. And you guys is the geometry governed anisotropy. And you see that the strength of this anisotropy is determined by the exchange and also by the this coefficient depends on the curvature of this system. And probably more interesting and intriguing term, it's the term which breaks the chiral symmetry, is geometry governed Zaleshinsky-Mourier interaction. So again, the constant of this effective Zaleshinsky-Mourier interaction is just a product of the exchange stiffness and the curvature. And the form and the symmetry of this guy, it's the same like the Zaleshinsky-Mourier interaction of the interfacial type. So, and we know that this interfacial Zaleshinsky-Mourier interaction leads to the helical structures, skirmilons, so we can look for similar effects in the curved system. So the message from this slide is the curvilinear geometry is a source of imagined Zaleshinsky-Mourier interaction. Now I would like to mention it's a very instructive analogy between this emergent interaction, this anisotropy and Zaleshinsky-Mourier interaction, and the classical mechanics. So we all know that the dynamics of massive particle in a non-inertial reference frame it can be described in the way where there appear new interactions, the corresponding forces, centrifugal and Coriolis force. And we know very well new effects which results from centrifugal force and Coriolis force. That is why it's useful to look what new effects appear due to this imagined anisotropy and Zaleshinsky-Mourier interaction in magnetic curved system. So I mentioned these two imagined interactions, so imagined anisotropy and imagined Zaleshinsky-Mourier interaction, and they corresponds to effects when the this interaction doesn't break the symmetry, they appear, this, for example, effective anisotropy on more general situations, important that they appear these effects of topological patterning. And this topological patterning, it means the formation of topologically protected textures in curved geometries with specific topology. Let's start with a flat film. We know that if the sample is small enough, that it supports the uniform or quasi-uniform magnetization distribution. But if we consider non-trivial topology, for example, spherical shell, and even if the shell is small enough, that tangential magnetization distribution cannot be realized. So instead, they always appear vortices. So it's a result of the curvature and topology. And the explanation is a well-known Harry-Ball theorem. And the physical reason is, in the case of the very thin spherical shell, is the exchange interaction, which leads to the appearance on three-dimensional anion state. If the shell is thick enough, they appear a Wall-Geek state, which is driven by magnetostatics. If we consider another topologies, for example, the topologies of the ferromagnetic tube, so this nanotubes supports different type of domain walls, so vortex wall and transversal wall. So if we consider toroidal shells, that its topology supports another topological pattern, so the toroidal vortices and poloidal vortices. Hyperboloid shell supports vortices and skyrmions, so it's dependent on the type of anisotropy and so on. And the last example here is the very interesting topology. It's non-orientable Möbius surface in the corresponding material Möbius ring. It supports different topologically protected domain walls. So another kind of effect are effects which break the spatial symmetry. It's so-called geometrical magnetic-chiral effects. There are two types of geometrical magnetic-chiral effects. So it's called a pattern-induced chirality break and a geometry-induced chirality break. So when we speak about a pattern-induced chirality break, so it means that the symmetry of the magnetization texture is so high that different magnetization configurations with different, for example, magnetic chiralities have the same energy. So it's the generated situation. For example, in this left picture, you see the ferromagnetic tube with head-to-head domain walls, but it's specific, it's a vortex type domain wall, and it can be magnetized counterclockwise or clockwise, and this texture is degenerated. So the break of the symmetry appears dynamically. It's driven by magnetostatics, and it means that if we apply the magnetic field, for example, in the z direction, so one of the wall moves faster than another one, and finally it leads to the so-called chiral breakdown. The situation can be very interesting in this curved nanotube, for example. They appear as suppression on the worker breakdowns, and for the very fast dynamics, they appear as Spintronic effect. One more example is again with these nanotubes in the vortex state nanotubes. It's a non-reciprocity of the spin waves. So you see that dispersion law is asymmetric. So the spin waves move in different directions, have different velocities. One more geometrical magnetic ion effect is connected with the geometry-induced chirality break. So what does it mean? It means that the geometrical chirality of the substrate the surface or the wire, it is influenced by the magnetization chirality, and this geometry-reduced chirality breaks occurs even in the achiral structures. For example, we already show this picture in the nice presentation of Denis Sheka. So if we had a planar structure, for example, this parabolic stripes, just parabolic stripes, we see that head-to-head domain walls has a preferable direction outward, and tail-to-tail domain wall have preferred direction inward. So it's they appear a phase selective pinning, which is caused by exchange-driven Dzeloshensky-Mourier interaction. And this was the strength of this Dzeloshensky-Mourier interaction was quantified experimentally by the measurement of the pinning field. Also, the coupling between the geometrical chirality of magnetic helix and the phase of the domain walls appear in these helix wires. So on the helicoid ribbon, they appear the preferable direction of the ground state. Very interesting situation takes place in toroidal shells. They appear due to this Dzeloshensky-Mourier interaction, these vortices and anti-vortices. Also, these geometrical effects leads to the selection of the winding number in different merons on a curved shells. For example, the parabolic shell supports vortices, while the hyperbolic shell supports anti-vortices. And in spherical geometry of the spherical shell, the exchange-driven DMI supports skirmions. The next example is the coupling between geometrical chirality, magnetic chirality, and the specific topology of the Möbius ring. So we know that geometrically there exist two Möbius, left and right, so with different geometrical chiralities. If we magnetize this Möbius ring, there appear a number of different magnetization states, like here on this picture. This depend on the geometry and material parameters. And I would like to mention here the situation when we magnetize the Möbius strip perpendicularly. So due to this non-orientable topology, this perpendicular state has a discontinuity. Finally, there appear a domain wall, and its domain wall is topologically protected. And what is interesting that the chirality of this domain wall, it means it is directed inward or outward, it is coupled with the geometrical chirality of the Möbius. So again, this exchange-driven Dzeloshensky-Mourier interaction here results in this coupling between the chiralities, geometrical and magnetic chirality. So in its not this Möbius is not a mathematical trick. So such Möbius states were fabricated recently by a Fabit technique. So the next example is about exchange-driven DMI, and I mentioned here the very interesting topological, localized topological texture was a skirmion. So we know that the in the flex structures, typically skirmions are supported by the Dzeloshensky-Mourier interaction, and here there are different mechanisms of the skirmion stabilization by the curvature, even in conventional materials without intrinsic DMI. So the first mechanism, small radial skirmions can be stabilized by the mean curvature. And the tunable radius skirmions in particular large radius skirmions, can be stabilized by the gradient of the mean curvature. And it's supported by the experiments. So already the first experimental picture you saw in the talk by Steven Asko. So it means that these pictures are self-organized cones or nano indentations, and after that the magnetic materials, perpendicular magnetic materials, were deposed on this non-magnetic substrate, and finally they appear topological magnetization texture, and the peculiarities of this magnetization texture is related to the geometrical properties. So again, due to these effects, geometrical, which I described. So the next example of geometrical magnetic chiral effects is mesoscale Dzerzhinsky-Murray interaction. The idea is following. So if we combine two Dzerzhinsky-Murray interactions, so if we consider material with intrinsic, so material Dzerzhinsky-Murray interaction, and extrinsic, which means a geometrical Dzerzhinsky-Murray interactions, two DMI are characterized by different scales, different directions, and different symmetries. So we have a lot of opportunities to tailor the magnetization properties of such materials by just geometrical manipulations. And that is why they appear a concept of artificial magnetoelectric materials, when it is possible to change the magnetization state by just changing the geometry of these helices or these spirals. And one more example. So if we consider a bump or a lattice of these bumps, so each bump can support two different skirmions. So the small radius skirmion is determined by the curvature, as I described, and large radius skirmion appears due to this mesoscale DMI, combination of geometrical and material DMI. And one can use it in perspective for encoding information with the skirmions, and applying magnetic field, one can switch one skirmion state to another skirmion state, and moreover, the ground state of this system is just this skirmion lattice, and we can reconfigure it. So up to now, we consider mostly local chiral symmetry breaking effects, and moreover, if we consider the flat structures, the non-local effects does not exist at all. And to understand the origin of the physics of these non-local effects, or non-local effects which are driven by magnetostatics, so we it is useful to use the language of fiction magnetic charges. So we know that typically in magnetostatics we use a volume and surface charges, but when we have a curved magnetic shells, so it is useful to consider to introduce three magnetic charges. So the tangential charge in flat system is correspond to the volume charge, the standard surface charge, and the new guy, it's a geometrical charge. So you see that is determined by the mean curvature of the system, so determined by the local geometrical properties, and also is determined by the normal magnetization component. So it's coupled geometry and magnetization. And very recently, it was also shown by Denis Sheka. So these non-local chiral symmetry breaking effects were validated experimentally in conventional samples. So it's a vortex state permalloy caps, but they are asymmetric. And due to this asymmetry, they appear a coupling between the helicity of the vortex texture and the geometrical chirality of the vortex string, because the vortex string is deformed to the helical configuration. And the details of this very interesting effect will be described tomorrow in the talk by Alexei Volkov. And now I would like to mention some current and future challenges of the curvilinear magnetism. So if we speak about fundamental directions, so I will mention here curvilinear antiferromagnetism. If we're speaking about applications, so I will mention here shapeable magnetoelectronics, curvilinear spintronics, curvilinear magnonics, curvilinear skyrmionics, and magnetic soft robotics. So the shapeable magnetoelectronics was already presented by the talk by Denis Sheka, and I will mention here a few other topics. And first, I start with curvilinear antiferromagnetism. It appeared very recently, so the first publication was in 2020. So in this first step were made for the curved magnetic antiferromagnetic chains. And in the contrast to the ferromagnetic system, here the, for example, single ion anisotropy in antiferromagnets, in curved antiferromagnets, leads to the appearance of the homogeneous Dioshensky-Maria interaction. So as a result, the curved achiral antiferromagnets can behave like a helimagnet, which very interesting properties. And for example, if we consider spin waves in antiferromagnets, due to this homogeneous Dioshensky-Maria interactions, they appear the hybridization of the spin waves. I would like to mention here a very nice review about curvilinear antiferromagnetism, and to the moment curved antiferromagnets are treated classically, so it means that no quantum effect, no frustration, and even no magnetoelasticity were considered. I would like to mention here curvilinear skyrmionics. So skyrmionics, which means the skyrmion-based electronics, is considered skyrmion as a skyrmion transport in the racetrack. And in the curved system, there appear new effects. For example, if we consider some bump structure, so the eigen oscillation of the skyrmion and the corresponding gyroscopical motion of the skyrmion is determined by the curvature of the system. So it gives the possibility to control the motion of the system by the curvature. And the right picture shows the drift of skyrmions. So the idea is similar to the situation with transport of domain walls. The automotion of skyrmions, so due to the curvature of the system, this results in a drift. So it's also important for the transport phenomena. And for sure in skyrmionics, so okay, so I will finish very soon. Thank you. So, and typically when we consider current-induced propagation of the skyrmions along the racetrack, so the influence of the curvature is very important. And in fact, for example, in tubular geometry, it allows to overcome the skyrmion Hall effect. And okay, so I will finish in one slide. So just last picture, so about bio applications. So there are a lot of very interesting bio applications. So it's magnetic soft robotics, in particular these magnetic swimmers are used in vivo applications. So They are used for diagnosis, for therapy, for microsurgery, for example, like here in this picture of the artificial fertilization. Okay, and now I will conclude that we consider different aspects of curvilinear magnetism, and we see that this mutual interplay between the curvature, topology, and magnetic ordering, it results in new effects. Some of these effects can be magnetochiral, and I hope that this balance and the synergy between the fundamental research, material science, and the applications, it will help to get new ideas and construct new devices. And finally, I would like to acknowledge several groups. First of all, it's our group written team, which is a joint group between Taras Shevchenko National University of Kyiv and Bogolyubov Institute for Theoretical Physics. And here I put names of people who were originally from this team and who participated in this project. And also I mentioned several other groups. First of all, the group of Denis Sheka, which we collaborate more than 10 years. And the last slide, for further readings, I suggest this recent book of curvilinear magnetism. Thank you for your attention.